somebody told me that you had asked this question really in some sense. I hadn't known that you had, maybe you formally asked this question, but at least you were interested in this question, why the minimax rates don't match the optimal recovery rates as the noise goes to zero.
Yeah, it's a very natural question. So
Yeah.
I
So
do
I'm
not
gonna
pretend that
answer
I
that
was the
question.
one who answered who asked that question, but it's a natural question. Yeah.
Yeah, and it
But
brings
as to
back,
recovery in general, this is the topic which we are working on a lot, I would say, and
oh, you are?
there pretty good progress in that.
So you're working on this a lot, so we should maybe at some time organize a Zoom between the people that you are working with and the people I'm working with, uh, because we probably have a lot of common questions, and you may
Yeah,
be, but
it would be nice for sure.
yeah,
Yeah. Yeah.
yeah. So at Texas A&M, it's Gergana and a guy named Jonathan Siegel. I don't know if you
Yeah,
ever
I
met
know
him.
him. If you remember, he even applied for job in South Carolina.
Right, right.
But these
Well,
guys, I mean, you know our department, so
oh, it's all screwed up. Here in Texas, we're trying to emulate South Carolina by screwing up as much as we can. But Jonathan is extremely smart, and
yeah, and he's a great guy. Yeah, I know.
yeah, yeah, he's really good. And so, and then we work a little bit with people at Wisconsin, Rob Novak. You know Rob, probably.
Yeah, I know him for a long time.
Yeah,
Yes.
yeah, and one of his postdoc former students, who's now a professor at UC San Diego. So
Uh-huh.
Rahul, he's one of the co-authors here, Rahul Parhi.
Hmm.
Yeah, so we have all kinds of questions on sampling, learning, and minimax, and a lot of open questions and things we don't quite understand yet. So,
Ron, I guess it's already 18, so
mhm.
probably it's time to start.
Okay, go for it.
Yeah. Okay.
You want me to just start talking, or do you
Yeah,
want me to?
let me just say a few words. I hope everybody can hear. So today we have our regular but online meetings of the seminar of artificial intelligence, and today's speaker is Ronald DeVore, and I'm pretty sure that everybody knows, and maybe even many of you have already heard his talks at our seminars or our conferences. And the title and everything you can see on the screen. So Ron, you're welcome.
All right, thank you, Volodya, and hello to everybody in Moscow. I had many great visits to the Steklov Institute in the past. It's a great place to go. Moscow is a great place to visit, but life's complicated now. To make such a long trip in the middle of the semester is not possible for me. So I'm forced to give this talk by Zoom. So you see the title of the talk. I'll explain what all these things mean in a minute. And please notice the authors of the talk. Uh, and then I also want to mention that it took me a long time to figure out, or us to figure out this, what's going on here. And during that period, we had many conversations with other mathematicians, some of which are listed here below. And in some sense, this whole subject goes back to work I did with Volodya Temnikov and Gerard Kerkacherian and Dominique Picard many years ago. So what is the problem? Uh, this is what I would say is the core problem in learning is you have a function f on some domain omega, and it's unknown to you, but you observe some data observations of f, yi. These are what you are given, these numbers you're given, which are values of f at some points in the domain, but polluted by noise. And your job here, so this is notation as we go forward, y of f, y equal y of f is the noisy observations. Our problem is to recover f in some norm x. See, we know f at the data points, at least in some noisy sense, but we'd like to know f everywhere on the domain. So we pick some Banach-based norm in x, and we ask to construct a function f hat. Our job is to use the data, the y's that we observe, to construct a function f hat that approximates this function f, which is unknown to us, in the norm of x. Now, classically, one typically chose x to be the L2 norm, but I leave open that choice for now, and in the end, I will choose any LQ norm for Q different than 2. Okay, so this is the fundamental question in learning, is at least this is the regression problem, and it's closely related to classification, but I won't speak about classification today. Okay, so if you were asked that question, and you're a mathematician, you immediately say to the person asking this question, well, look, I can't answer the question for you. I need some more information. What more information do I need? Well, first of all, I need some more information about f, because if f can be any function, then knowing its values at these points is not sufficient for me to tell you anything about what f looks like away from the data points. That is the norm of f minus whatever function f hat you create, could be arbitrarily large. So you need more information about f, and the usual way we handle this is we say, well, we need some what we call model class information that f has some properties or some extra knowledge about f. You may think, okay, f is in a Lipschitz space, or f is in a Sobolev space, or f is some sparsity, or something about f. Okay, and we call that model class information. And what a model class information is knowledge that f is in some set k. K is the model class, and k is a compact subset of x. So that's the first thing you need, is you need information about f. But since you're dealing here with a noisy since we're dealing here with a problem where the data is polluted by noise, I also need you to tell me, well, what do I know about this noise? What do I know about these eta i's, remember, that polluted f? I observed not the value of f, but the value of f plus noise. So what do I know about that? Well, we will assume, and this is sort of standard in statistics, that the noise is identically distributed, independent Gaussian observations, okay? So with a variance sigma squared, and sigma is going to be important for us. The behavior of this problem or solution to this problem as sigma varies is going to be important. So this is the information I'm going to have about f. So from the point of view of how much have I narrowed down the possibilities of what f can be, is really I know that f is in the set ky, that is, it's in k and it satisfies the data, the noisy data, right? And I know the noise. Okay, now we're interested to take this information. so these two pieces of information about the model class and the noise, together with the data, and construct an approximation f hat to f. Well, how are we going to do this? Through some numerical algorithm. So what is an algorithm in this case? Well, it's going to take this y, these were our observations, and create from it a function f hat in x. So it's a mapping from Rm. M is the number of observations, if you remember, that's important. How many data sites do we have? And A is such a mapping. And now what would be the performance of this algorithm? So you construct some algorithm, how to do this problem. And how would we typically measure the performance? We look at, given the data observations, we would, and the f hat you created, which would be A of the data, right? You take A of the data, that's your f hat. And we look at its norm in x. Now, its norm in x is going to be a random variable because the noise is random. So then we would take the expectation of this, and this would be a measure of the performance of our algorithm on a specific data given. And then we take the soup over all f in class. This is in the class K, because this is all we know about f is that it's in the class K. So our enemy could have been giving us any data for any f in K. So this is where the word max comes in, because you're looking at worst possible performance. You're saying, okay, I've created the algorithm, I've told you what to do, and now when I check how well I'm doing, my enemy can give me any f and k, and he can give me any sigma, which is this normalized Gaussians. Okay, so this is the error of a given algorithm A. And now if you look at, so we're interested in the problem here of what's the best algorithm? Okay, can we say something about, okay, here's the best algorithm, you can't do any better, go home, I've solved the problem, there's nothing more to be said about this. So that's our interest, is what is the best algorithm, what is the performance of the best algorithm? What is the smallest error we can achieve? And what algorithm would achieve that smallest performance? Okay. Now, this error, I want to go back to this minute. This error depends on x, the data sites. Remember, x are the positions of the points in the domain omega. And, you know, maybe I have no control over where you have chosen the data sites, but that causes a big problem, because the error will now depend on the data sites, and you may have good data sites, bad data sites. You don't know. So what we want to do is we want to say, well, let's assume that the data sites were optimally chosen, the best sites. So we fix a budget M, that's the number of measurements we allow, and we assume that the xi's are optimally chosen. Okay, now there is another view of this, is to assume that the xi's are randomly chosen, but I'm not going to deal with that here. So the xi's are optimally chosen. So if the xi's are optimally chosen, you can intuitively have the feeling that typically they're equally spread out in the domain omega, unless you had some more information about this set K that told you otherwise. You would assume the xi's are sort of equally spaced out. But in any case, if the xi's are optimally chosen, now you have a performance that only depends on M, and X has gone by the window because this was the optimal selection of data sites. Okay, so this EAKM sigma is a measure of the performance of the algorithm. And now we're interested in this case. So for the xi's are fixed, but they were optimally chosen. Then we are interested in the best algorithm. So we take the infimum over all algorithms here, and we denote this optimal error you can achieve by R star. So it depends on K, the model class. It depends on your noise sigma, and it depends on M, the number of points. But it doesn't depend on the positioning because you fix the positioning as the best. This is called the minimax estimation of what the space X you measure error in. Now, I'm going to get to what has puzzled me about this question. There are two theories that have emerged. One is one which is called optimal recovery, and perhaps most heavily studied in what's called the IBC community, information-based complexity, where you assume that there's no noise. Sigma is equal to 0. So if you come back up here and you assume sigma is equal to 0 and look at the R star Km, this is the optimal recovery of this model class K using M observations, point samples. Okay, so that's one, optimal recovery. And of course, Volodya has studied this. I've studied it. A lot of people have studied this. The statisticians look at the general case where sigma is bigger than 0, and they call this minimax theory, as I've already mentioned. And I'm interested in, well, what's the relationship between these two theories? One would think, well, minimax is more general because it's not requiring the noise as 0, it's allowing any noise. You would think that the minimax theory would subsume, that is, contain all the results in optimal recovery. You would say, hey, you guys in optimal recovery, I'm not interested in your case because I handle the general case of sigma, and your case is just a subcase of it. So you would think that, but this is far from the truth. So I want to understand what is happening in this setting. Okay, so I've stated this problem for general model classes. And of course, I would love to have a result that holds for general model classes K. We're far from being able to do this. What we can do is for specific model classes, we can discuss minimax theory, optimal recovery, and give you some results. So we say not only do we know we need a model class, you have to sort of tell me the model class, then I'll develop the method of recovery, the algorithm, dependent on that model class. So in this talk, I'm going to take as model classes K, Bessoff or Sobolev, the unit ball typically of a Bessoff or a Sobolev space. Now I assume that since I'm in Moscow, everybody knows this, right? But if not, you just put on the side, oh, I have to learn what this means. Roughly speaking, when you look at a Bessoff space, the two main parameters are this S here in the top and the LP, P, and you can view this as a smoothness space where the functions have smoothness of order S in LP. It's like S derivatives in LP, but you have a secondary index tau that gives you a finer gradation of these spaces that's useful in some context. So this is what I'm going to assume about my model class K. Now, I'm talking about taking point values of functions in K. Now, if I take a general Bessoff class, or even a general function in LP, its point values make no sense, right? So I have to assume something about the little more about K, so point values make sense. And so what I assume about K is that it's a compact subset of continuous functions on omega. And that imposes the condition that the smoothness S is bigger than D over P. So you'll get a compact subset of C of omega if and only if S is bigger than D over P. So that's an assumption I'm making right from the start. I'm looking at Bessoff balls, but only in the case that S is bigger than D over P. And now it doesn't matter. The secondary index is not going to play a role. You'll see in the results. Okay, so when S is bigger than D over P, in fact, the function F will be a Lipschitz function with smoothness S minus D over P, whatever the difference is between S and D over P. So if you can have a feeling for what type of functions we're dealing with. So I'm not looking at this class, I'm assuming more because my set K embeds into lip delta, okay? All right, and here's the usual picture of what's going on if you look at smoothness spaces where this is LP on the x-axis and the smoothness on the y-axis, and I have a smoothness space S derivatives in LP, and then Sobolev embedding tells me that it ends up being a function which has some smoothness in C, and the smoothness is that it's Lipschitz of order delta. Okay, do you want me to pause here, Volodya, and see if anybody has a question? I don't want to lose anybody here. You know, one of the disadvantages of Zoom talk is that you don't see the audience and you don't know if they're following what you're doing.
Yeah, if there are any questions at this point, let's ask.
Yeah. Any problems with anybody? Do you understand my problem? You know what my classes are, you know what the noise assumption is, and what minimax problem is. Yeah. No
It looks
questions
like,
from.
yeah, no good, but yeah, to my opinion, it was very clear. So let's go
Okay.
ahead.
All right. All right. So I'm interested in. Well, let's first talk. What is the optimal recovery rate? That is, if the noise is zero, sigma equals zero, then it's. Here's the theorem that the optimal recovery rate when sigma is zero is m to this power minus S over D. Remember, S is the smoothness order. P is where we're measuring smoothness. And now I'm taking the error, by the way, in an LQ norm. That's what Q is. So X is LQ. Sorry, that's not written on the slide. X, the Banach space where I'm measuring error, is in LQ. And this is the optimal recovery rate. And people that work in the subject say, yeah, of course, we all know this. Everybody knows this. And this is not too hard to prove. And if you look at this, I guess the most general treatment of this would be in this paper, Erich, Novak, and Treble, because they do this for any bounded Lipschitz domain omega. And they show how to create an algorithm. And the thing I want to point out about the algorithm, so given this case, you would be observing a function f and its true values at these points xi, right? And the xi's are sort of equally spaced in omega, and you have their true values. And then the way you would recover f is you would use something like quasi-interpolance, as you'd take little bump functions, which are 1 at the data site and then fall off to 0 away from the data site. And these bump functions, if I call them phi I, you would then just take a function of this form, sum I equal 1 to m yi phi I. So there are many ways to do this optimal recovery, and this is well covered in the literature, and everybody working in the subject certainly knows this result. Okay, what about the, let's see what I'm doing on this slide. I'm going to tell you a way of doing this optimal recovery. Before I go to Minimax, I'm going to give you one particular way of doing optimal recovery, which will be useful when we turn to Minimax. So that's what I'm going to describe on this slide. And what I want to do, and for the remainder of the talk, assume that omega is a cube in RD. How to generalize this from a cube to general omega, I'll talk a little bit at the end about that. So here I want to put myself in a very concrete setting that omega is this unit cube in RD, and my data sites are on a tensor product grid with spacing 2 to the minus n. So I think I show. So look at the left here, this. So the data sites are the vertices of these small cubes here, and these small cubes have spacing h, which is 2 to the minus n. So I have, in essence, if I look at all the vertices of these small cubes, that's where I'm going to observe f. And there are 2 to the n d, right? The number of data is 2 to the n d because there are 2 to the n d cubes, right? All right, so that's my data sites, tensor product grid. And what's neat about this is you can view the partition you have here, whoops, this partition into cubes as part of dyadic partitioning. You know, in dyadic partitioning, you start with the cube, then you divide it into cubes of side length a half, and then a fourth, and then 1/8, and then 1 over t to 2 to the k. And this is what the dyadic partition corresponding to k equals n. But I'm going to utilize at different times the coarser dyadic partitions. So, for example, the first dyadic partition would just be divided into these biggest cubes of side length a half. Okay, so let's dk denote the dyadic partition, and of course our data is given by the vertices of the cubes in Dn. But for any cube I in dk now, so it could be a coarser cube. Why do I want to use coarser cubes? Because I have more data. If the cube is bigger, bigger, I have more data on that cube. If I look at the cubes I in Dn, I'd have very little data, right? I just have data at its the vertices of that cube, which is not enough data. So if I look at a cube in dk, then I have this number of data points, right? 2 to the n minus kd. And now what am I going to use to approximate f, my algorithm? My algorithm is going to be, I'm going to create a piecewise polynomial to do the approximation. So my f hat is going to be a piecewise polynomial of order r on some partition. And the partition I'm going to take is dn minus r, where r, little r, is going to be the degree of the polynomials that I want to use. So maybe I haven't been real clear on this. When I'm going to, my approximation to f, my approximation to f is going to be this last line, sk of f. That's going to be my approximation. If I were doing optimal recovery, I would take as sk of f this piecewise polynomial. And what is the piecewise polynomial? First of all, I would take k equal to n minus r. Why do I change from n to n minus r? I need a little more data than at level n. So little r is a small number. It corresponds to the degree of these polynomials. What degree do I pick of the polynomials? They have to be bigger than the s, the smoothness that I know. I know my functions have smoothness of order s. So I choose r as one, greatest integer in s plus one. Those familiar with Besseff spaces know that this is how you choose r. And now I look to create a piecewise polynomial on this partition, dyadic partition at level n minus r. So it's a little coarser than the partition where I have the data. Okay. And what is the polynomial in this partition? I mean, in this approximation. So it's a polynomial on the cube I, right? What is the polynomial? I simply take the least squares approximation to the data from PR. So I have enough data. I have more data than the dimension of PR, and I take QI to be the polynomial that is the least squares approximation to the data on this cube I. Okay, so I think maybe I should pause here again because I don't think I did a great job at explaining this, but do people understand what I'm taking for my optimal recovery? Volodya, did you understand what I'm taking?
Yeah, sure, I understand.
Okay,
Yes.
all right. So if you understood, then everybody else should have understood.
Yeah, I hope so.
That's
Yeah.
my usual joke, right? Okay,
Yeah.
so I'm creating a piecewise polynomial. This is going to be important because in minimax theory, they usually use wavelets. I don't want to use wavelets. I'm using piecewise polynomials. All right. So now let's talk about minimax. So that what I just told you, this piecewise polynomial construction, would solve the optimal recovery problem. So see how easy it is to solve optimal recovery? You take the data, you take this cube, you take its least squares approximation by polynomials, and then you take as your function f hat a sum of these a piecewise polynomial on each of those cubes. Okay, now let's look at minimax. So this should read minimax, not minmax, but minimax. All right, so if I ask you what is the minimax rate in this case, or you'll say in your statistician, you'll say, well, this was solved by Donahoe Johnstone years ago in a very famous paper. And I want to review what that paper did. So what that paper did, it says, okay, you're interested in minimax, and remember we have this noise level sigma. We have Gaussians with variance sigma squared. Now they do the problem only when d is 1, so they had an interval 0, 1. And they proved that if you look to recover elements in a Besseff space, this is the minimax rate, m to the minus s over 2s plus 1, right? Read their paper. You probably have already read it since it's such a famous paper. So I look at that result and I look in their paper and I say, what the, something bothers me here. I don't see sigma appearing on the right-hand side. So how should I interpret this result? And if you look carefully, this is the way you interpret this result. What their result is, this wiggle here, this is important. What does this wiggle here mean? It means that there exists two constants, the C of sigma and a capital C of sigma, and that the optimal recovery rate is less than this and bigger than or equal to that with these two constants. But they don't tell you what the constants are. So their theorem is like, I'll fix sigma and then I'll have this. Now you can argue with me and say, well, they had some statement in here and so and so. It doesn't give any real good information about these constants, capital C of sigma, little c of sigma. So if I look at minimax, and if you say to me, well, we know the minimax rate for the Bessoff ball in L2, even though it's only one-dimensional, so I should know the optimal recovery rate. But I can't let sigma tend to 0, right? Because I don't know the constants. And even if you say to me, well, maybe they can prove this with bounded constants, that can't be true. Because if I let sigma tend to 0, I get this rate, and I know the optimal recovery rate, and it doesn't match this, right? They don't match. In fact, this rate is always bad, because notice that this rate is always a number which is smaller than a half, right? It's m to the minus alpha, where alpha is smaller than a half. Whereas in optimal recovery, you can have very, very fast rates. The alpha is much, alpha could be huge if you have enough smoothness. So this bothers me, and that's the start of this sort of project. So here are a few things that bothered me about, and then there are a lot of papers written on minimax for Bessoff classes and trying to generalize what Donahoe and Johnstone did, and we've tried to find all the papers that did. There's a chance we missed some, but I don't think so. But here are the things that I want to make some further remarks on the minimax that will make clear some points. They really treat, in Donahoe Johnstone, really treat the case S less than 1 carefully. In that case, you can use Haar wavelets. So they're going to use wavelets to construct their function f hat. They're going to create f hat as a sum of some linear combination of wavelet functions at a certain dyadic level, similar to what I was doing in the optimal recovery case. Well, when the smoothness is less than 1, you can use Haar wavelets. What's nice about Haar wavelets is they're supported in your domain, right? In their case, their domain is 0, 1, and the Haar wavelets are functions, and they live on 0, 1. But if you go to higher orders of S, and you want to emulate what they did for Haar wavelets, and you want to do this using more general wavelets, these wavelet constructions are much more complicated. The standard wavelets would not be supported on 0, 1, so you'd have to do some massaging at the endpoints of the interval by changing the wavelets near the endpoints. And the constructions for doing that started with Cohen-Dobucci's Fauveau. But nobody in statistics actually, that I can see, carries this out. They just say, well, you can do this. But there's some detail here to actually carry this out, this construction. If you want to generalize from S less than 1 to general S, you have to do this. All right, one other point. In Donahoe Johnstone, their algorithm here, they prove that it must be a nonlinear algorithm. How you map the data sites into your function has to be a nonlinear mapping. This should be contrasted with the case of optimal recovery, where we had back here, our mapping could be linear. In fact, my mapping in my construction using piecewise polynomials is linear also. So there's a distinction here that why. So you ask the question, why does it have to be nonlinear for minimax, but it could be linear for optimal recovery. What's going on there? All right, let me mention that it seems that the most general paper that's trying to do this is this paper of DeLone, Juditsk, and they claim they have the minimax rate, all right, for the Bessoff ball in any LQ space, and generally speaking, this alpha would be S over 2S plus D, but for certain Q, that has to be changed. It's not that. But if Q is 2, it would be M to the minus S over 2S plus D. So they claim to prove this in this paper, and I would say, yeah, sort of they push under the rug what you're going to do for wavelets when S is big. How do you construct the wavelets on so that they all live on this cube? You have to do some massaging near the boundary of the cube, and they shove that part under the rug. They don't discuss that in detail. Okay, so our view is that we're bothered by several things. One, the optimal recovery rate does not follow from minimax bounds. If you look at minimax bounds and try to let segment tend to 0, you won't get the optimal recovery rate. And the reason is the optimal recovery rate has constants that depend on sigma, and you don't know what they are. A second question is, well, how do you extend these results to more general domains? Because you're using wavelets. Now, if you're going to take, instead of the cube, a general domain omega, you're really going to be in hot water if you have to use wavelets. And it's going to be a complicated construction. All right. And then, in addition, I'd like to understand why in the optimal recovery I can use a linear map, and in minimax I have to use a nonlinear map. Okay, these are the questions I want to ask. So now I'm going to explain what we proved, how we proved it, and how it answers some of these questions. Oh, unfortunately, I don't know why this cuts off here, right? It's cut off, I'm sorry, the left part. So here's what we prove. We're going to work on the unit cube again, 0, 1 to the D. We're going to have as our model class this Bessoff class. And we're going to be interested in the optimal, the minimax rate for a given sigma. And here's what we're going to prove about it. We're going to prove that it behaves like this. This part here, this first term, and the second term is, roughly speaking, the minimax rate that they claim, right? I see some things flashing on my screen about internet connection. I hope I'm still doing okay and you're there. Am I still live there for you, Volodya? Yes.
Yes, you are,
Okay.
but it was a little like maybe 1 minute or so a break. You were frozen, probably because of this internet. But I think it was just
Should I
for
go back or anything?
no, that was on this
Okay.
slide. So I think
All right. All right. So here we go. So this is the new result we're claiming. We're claiming, here's a theorem, that the minimax rate, sorry, it's chopped off here, why I don't know, but this should be R sub M K sigma, minimax rate, in LQ is this. If you take Q equals 2, this power alpha is simply S over 2S plus D, if Q is 2. So you would say, well, that sort of matches Donahoe and Johnstone, because they get sigma squared over m to the 2s plus 2. And I was saying this max should be a min, not a max, sorry. Because if sigma tends to 0, this term will disappear if I have min here, right? That's why I knew it was a mistake. This should be min. And as sigma tends to 0, this term goes to 0, and you get the optimal recovery rate. And when sigma is bigger than 0, you get a rate, but it may be better than what they claim is minimax, sigma squared m over alpha. For some m's, it will be better. Only when m is sufficiently large will you get the rate that they claim. So I'm claiming that here is the true minimax rate. This is a finer description. And in this comparison, the constants, and there's the wiggle here, the constants are absolute constants that depend only on the P, Q, and S. They don't depend on M or sigma. So this result is true with absolute constants once P, Q, and S are fixed. Okay, so that's our claim. And we actually give a result in probability, but I see that I'm going to be have a problem with time, so I'm not going to spend too much time on this. But it's interesting that we're able to obtain a result in probability, and now this should remind Volodya of the work we did with Dominique and Gerard, where we got results in probability. And we always liked results in probability better, because if you look at a result in expectation and say, well, tell me what this means as the noise gets worse and worse and worse, what you find out is that you can only use Markov's inequality, and you get a very slow decay as t in this theorem would get bigger and bigger. But in reality, we prove that it decays like e to the minus t to the alpha, or t to the beta for some beta. Okay, so there are results in probability, but I'm not going to spend a lot of time on this because time is going to run out. I don't want to run out of time. So I want to explain how we prove this in 5 minutes. Okay, so as I told you, the result, the actual minimax rate here in the primary, so the minimax rate, this number here, S over 2S plus D, this part of it, will depend on S, P, and Q. But if you take Q equals 2, it doesn't depend. So think of Q equal 2 from now on, okay? Take L2. Because when you go to LQ, you have to say, well, now I could get a different rate for different values of S and P. So think of Q equals 2. Then the rate is always S over 2S plus D in this term, all right? Or back here in expectation, the rate here is S over 2S plus D. Okay, if Q is 2, this rate is always S over 2S plus D. If Q is bigger than 2, then you're going to have some cases depending on how big SP are compared to Q. All right. So we call that the primary case, and I'm going to just describe that. And I'm going to say, well, how are we going to create our approximation? Here's what we're going to do. We're going to do the same construction I had for optimal recovery. When I have this dyadic partition, I'm going to have these squares, and I'm going to have data on the square, and I want to construct a piecewise polynomial. And the way I construct a piecewise polynomial, just as I did in the case of optimal recovery, I'll take the least squares approximation to the data. So again, the polynomial will be the best least squares approximation to the data on a given cube I, right? So I is a dyadic cube and PI is a least squares. Now, in this case, the difference between this case and what I discussed before is now I have noisy data. Before I had noiseless data, right? Oh, I'm sorry. Maybe I'm not completely careful. PI is the best least squares approximation if to noiseless data. I don't know PI because I don't have noiseless data. PI tilde, when you see a tilde, that means the data was noisy. When you see no tilde, it's a theoretical assumption. It's saying, okay, if you had noiseless data, then this would be the least squares approximate. So what I can construct from my given data are these PI tildes, and then I construct as my approximation to F the sum of the PI tilde chi I over this dyadic level at level n minus r. All right, so this just says, well, you know what, you can represent the least squares polynomial approximation in terms of a basis. So if you're on a cube I, there is a basis of polynomials, qij. J is 1 to rho is the dimension of PR. Every polynomial can be represented in this way. And this is just the QIJs are an orthonormal system with respect to the empirical measure on the cube. All right, so how am I constructing my approximation F hat? I take the dyadic partition at level n minus r, and I take piecewise polynomial on this dyadic partition. How do I get the polynomial pieces? I take the least squares approximation to the data on the cube. So is that clear? So this is how I'm going to construct my F hat. I'm going to take cubes, dyadic cubes at level n minus r. Remember, that's a little coarser than the finest level. And I'm going to take, I have enough data on that cube, and I take the approximation, and I'm going to, well, sorry, but this isn't quite correct. So we're going to create a piecewise polynomial on this partition of order n minus r, but we're not going to do it this way. I'm sorry, this was incorrect. I have to do it in a multi-scale way. So here's what we're going to do. What we're going to do is we're going to take dyadic partitions at levels k equals 0, 1, 2, 3, up to n minus r. If I wanted to create a piecewise polynomial approximation to f on that dyadic partition, I could use least squares, and I would have these sk would be my piecewise polynomial approximation to f using piecewise polynomials on the dyadic partition dk, right? But now I'm going to have noisy observations, so I do the same thing, and I would get something called sk tilde, which would be my piecewise polynomial at level k using the noisy data. Now, what's good about sk tilde is that when k is small, you have a lot of data on relatively big cubes, and the error due to the noise will be very small, statistically small, because you have a lot of data, and the law of large numbers says, well, because you have this assumption on the data, it'll be very small. Okay, so I will get to the point. So if you know Donahoe Johnstone, you know the way they do it is they numerically try to compute the wavelet coefficient of the function, and they get a noisy coefficient, and then they try to denoise the coefficient, and they do it by thresholding. What we're doing is we from the data, we get a noisy polynomial on each dyadic cube. And we want to denoise that noisy polynomial. And the polynomial has certain coefficients, and those coefficients turn out to be vectors in LP, where we have some information about their LP norm. So I'm sorry that I'm feeling a little rushed, so I'm not doing a real good job of explaining this. But here's what we have. We have a dyadic partition, and we're looking at partitions of level 0, 1, 2, etc. And in the usual multi-scale way, we can represent F as a sum of piecewise polynomials on these finer and finer partitions. And at each level, what we're doing is we're adding detail to the given approximation at level K. We add detail to get to the approximation at level K plus 1. We emulate this in the noisy situation. Now we have a noisy multi-scale decomposition, which you can think of as like wavelets, right? And we're now going to take our noisy polynomial on each cube, and we're going to denoise it. The way in wavelet theory, you take the noisy wavelet, and you really only have the noisy wavelet coefficient, and you try to denoise it. So that's the issue. I think now I should not try to describe in too much detail how we do it, but I'll just mention a problem, a research problem that you can think of that is at the core of this whole subject. And it's a finite dimensional problem. And here's the problem. Suppose I'm given a vector V, okay, a vector of a certain dimension, L. L is the length of the vector. And suppose I know the norm of V and LP. That's the information I'm giving you. And I'm telling you that I'm going to give you noisy observations of this vector, where the noise eta are Gaussians with a certain variance. I'm not going to tell you they're independent. If they're independent, it's still interesting, but our results don't require that these observations are independent of one another. Now, if I say to you, this is the setup, how should you recover Vn in an LQ norm? Do you know the answer to this? How would you recover V in an LQ norm? So this is the fundamental question. And the answer is that you should take the vector and the observations you have, which are noisy, and you should threshold these observations at a certain level, lambda. And the level will depend on the L. And the question is, what should this threshold be? How big should you choose lambda? It should depend on sigma, and it should depend on L. And that's the problem basically that we solve, and it tells you what threshold to pick. I don't want to go through the details because I'm running out of time. All right, so I skipped that. So this fundamental question I want to add that I mentioned here is at the heart of what we're doing. We solve this question, and then we apply it to our multi-scale decomposition, and then we know how to denoise these polynomials on each cube. Let me say a couple more words about this before I leave this slide. We make this assumption that the norm of V and LP, that we know this, and we want to recover an LQ. This is like our model class assumption. Think of P less than Q, right? Then knowing the vector is an LP implies that it's an LQ, but it's actually, a small set in LQ if P is small, right? Mm-hmm. And so this you can view as your model class K. This is the norm you want to recover in, and you have noisy observations, so you're trying to solve this. If you change this requirement on your vectors to be more general requirement on vectors, that the vectors lie in some set in RL. And if you could solve that problem, that would go a long way for giving a theory that for which you can get optimal recovery from minimax in more general theory than just Bessoff spaces. Our results currently are only for Bessoff spaces. All right, I'm sorry I screwed up a little bit here. I wasn't so clear. I talked too much in the beginning and then found myself crowded at the end. So this is the last slide. I just want to say what we did, even though it wasn't completely clear. What we did is we gave for the domain omega equals 0, 1 to the d, and for Bessoff classes, we gave a new result for minimax rate, right? I won't go back to it unless you ask me to. And that new result for minimax rate is an improvement over all the results in the literature because we have a more precise description of the minimax rate. And it's so precise that you could let sigma tend to 0 and get the optimal recovery rate from it. We did not use wavelets in doing it. I think this is an advantage because if you use wavelets on a general domain, you have to do some massaging at the boundary of the domain to give a new system that isn't the original wavelet system. And people typically do not give the details of how this goes, and I claim it's quite complicated analytically to handle this. And another thing we did is we gave results in probability, not just expectation. So you can get the expectation results from our probability results, but these results in probability are stronger. So these are the things we did, and we did it all with piecewise polynomial and least squares approximation by piecewise polynomials. And that part I didn't explain very well. I apologize, but I got a little bit rushed there. Okay, so I think I should stop here, Volodya, because it's an hour and I don't want to abuse the audience and use their time when they're anxious to leave. Okay, thanks.
Okay, Ron, thank you very much. Now, I understand that you're kind of critical to yourself, but I think with all these explanations, even with those couple of moments when the connection was frozen, I think you did a great job. So at least it was easy to follow. And yeah, everybody, is it published already, or at least in the form of preprint?
Yeah, it's almost completed. The writing. We're writing the paper now, and it's almost finished. The part to do the probability result is complicated. To do the result in probability is technically difficult to write down. So
Yeah.
that's where we're trying to make it as elegant as possible so that the reader can understand it without seeing a lot of formulas and all that. But it's almost done. Within a few weeks, the paper will be finished.
Okay.
Yeah.
Are there any questions, comments?
Yeah, can I ask a question, please?
Oh,
Thank you for a nice talk. I'm not an expert in the field, so maybe it will be a stupid question. The question is about slide number 19. 19. Yes. So
yeah.
What does it mean precisely to threshold a component at a level lambda?
It means that if so here's what the slide is saying. You have a vector V, which is a vector with L components, and you know it's LP norm.
Yeah.
But you don't see V. You only see a noisy version of V. So
yeah, I understand this.
Yeah.
What does it mean to threshold?
That you look at the component of V, let's say the first component. If that component is bigger than lambda, right?
Yeah.
Then you're going to make it, you're going to threshold its value down to lambda.
I see.
So say lambda was 1, just for sakes. If the vector has value 7, you're going to decrease its value to 1. So you
Okay.
decrease, you take the minimum between the value, the actual value of the vector and lambda. You never allow, well, the idea is, of course, that if the noise is big, you recognize that it's big because you know that the true component should be small, right? I mean, you know that the true component of the vector lies in little LP, right? The vector lies in little LP. So if components are too big, you're going to threshold them. You're going to bring them down. But
Now I see. Yeah.
yeah, but yeah, okay.
And so
But I
now,
want to observe that in our application, we're doing this multi-scale. So at every scale, we're thresholding. So it's like in Donahoe Johnstone, they observe the wavelet coefficients, which are a vector, and they know something about, from the Bessoff classes, they know the vectors in some LP space, and then they decide what level's the threshold and to bring the value down to get rid of the noise. So thresholding is sort of like trying to remove noise when it's apparent that the coefficient has noise.
okay,
So,
now when I understand what this means, could you please briefly reiterate what is your prescription to choose lambda? How to choose lambda?
yeah. So that was back here. So we said, oh, okay, how are you going to choose lambda? So we looked at this problem and said, okay, if that's the information we have, how should we choose lambda? What should the threshold be? And the first thing we said was, well, let's see what the error would be if we threshold it. What, you know, to understand how to choose lambda, we should say, what does the error look like? So if you have a number x and you observe x plus epsilon instead of x, and then you say, well, I want to improve my approximation to that number, and I'll threshold at some level. This is the error you're going to obtain. There will be two components in the error. One will be this, which is in our case, if you think of epsilon as being a random variable, a stochastic quantity, this part is deterministic, and the second part is stochastic. So what we did is we said, well, we want to understand what thresholding does. And if you threshold the vector, we prove that when you look at the LQ norm, after you've thresholded, you'll get two quantities, A lambda, depends on the level lambda, and B lambda. A lambda is a deterministic quantity. Don't try to understand it all immediately. And the B lambda is a stochastic quantity, which relates to just thresholding Gaussians. And now what we do is we say, okay, we want to choose lambda to make these two numbers, A lambda and B lambda, as small as we can, right? You're asking me, how do you choose lambda? What is the formula for choosing lambda? I can't say it's a trivial problem to decide how to choose lambda. What you do is you look at these two numbers, A lambda, and you look at this B lambda, and you try to make both of them small. So what's going to happen is that A lambda is going to be small if lambda is small, and B lambda is going to be small if lambda is big. And so you sort of try to balance these two. This is called what do we call it in statistics? This balancing bias variance trade-off. This is like a bias, and this is like a variance, and we try to make both of them about the same. So that's how you choose lambda. Now you say, well, what is the value of lambda? Look in the paper, and we have an explicit, we solve this problem of making A lambda like B lambda.
Okay,
So
Thank
that
you.
tells us what lambda is, and lambda looks like, yeah, you do no thresholding for a course. When you're on course cubes, you do not use thresholding. The reason is that your observations are quite accurate because of the law of large numbers. But as you move to smaller and smaller cubes, you have less and less data. And at some point, you begin to threshold. And when you start thresholding, you decrease the threshold by a power of 2 to the minus alpha at each dyadic level as you march along. Okay, those were good questions, but you'll
Thank you.
have
Okay, yeah, getting better understanding. And are there any more questions?
Yeah, can I also ask a quick question? So, thank you, very interesting. So, are you also, my intuition is that there might be some kind of optimal scale here in this setting. So, if you consider, as you describe, if you move to coarser scales, then you decrease the variance, but increase the bias, presumably. So usually in this setting there is some optimal value. So does it
yeah,
occur in this?
that's exactly what's happening, right?
Mhm.
That's this bias variance trade-off as you move in dyadic scales. But we have to solve this problem for every dyadic scale. At
Mhm.
every dyadic scale, we have to say, how do we threshold? We're not just picking one dyadic scale. At every dyadic scale we threshold. So we pick the dyadic scale and we say, what should the threshold be at that scale? So lambda sub k. And how do we do it? And your observation is correct that the bias is big and the variance is small. And what we're going to choose the threshold to make the two terms in this estimate here, which I haven't explained in detail, to make them about the same, to make A lambda and B lambda about the same. So at every dyadic level, we're going to do this trick of balancing the A lambda, which will depend on K, because we're at dyadic level K. So remember, V is a vector at dyadic level K. It has a vector of a certain length.
Okay, so this you cannot just choose one scale, right? So you need to
No. For each dyadic level has a different threshold. So, and as I said before, when you're at very coarse dyadic level, you don't threshold because the noisy observations are actually very accurate. I mean, accurate enough because you have so much data, you can figure out the true value of the coefficient from the data because you have a lot of data, and the law of large numbers says that you can get rid of the noise. So, by the way, it's nice to meet you by Zoom. I see that you're Yuratsky, right?
yeah, nice to meet you. Yeah.
Yeah, the guy that's written a lot of papers on neural nets, deep learning. Yeah, you're that
Okay.
guy.
Yeah. Thank you.
Yeah.
Yeah.
Okay. Nice to meet you. I
Yeah.
like your work. You're
Okay. So thanks very
a
much.
clever
Yeah.
guy, and nice to meet you.
Yeah,
Okay.
hopefully there will be a chance to meet in person. So,
Mhm.
but
Yeah,
we'll see.
he's an impressive guy, Volodya. He's done some
Yeah, I know. I
complicated
agree, absolutely. Yeah.
complicated
Okay.
stuff. So,
Okay. Thank you very much. Yeah.
okay.
Other questions? Are there any other questions? So I have one question, but this is kind of very general. I understand that you consider kind of a model class and model setting, and you restrict yourselves to Gaussian noise. How important is that?
Ooh. I mean, you could definitely take other tail bounds. I mean, the important thing in Gaussian is the tail bound. Certainly, you could do sub-Gaussian.
Yeah.
But if you want to go to Laplace or different tails for could be done, I guess. But all this is quite technical when you get to the point of how to threshold and what the thresholding gives, especially if you want to do it in probability, it becomes quite difficult.
Yeah,
So-
because you need the concentration measure inequalities in that case.
Yeah, exactly, and also, yeah, it's just a lot of balancing.
Yeah,
It's complicated.
yeah, okay.
But what I would like to point out, Volodya, is that assuming, just take vectors in RL and assume that the vector lies in some set K. And if it's K is a nice convex set, for example, and now I give you noisy observations, how would you denoise? The natural way would be to use maximum likelihood estimates. You would project,
Mm-hmm.
when you're outside of the body, you would project back onto the body. This is the right way. This is not correct for general convex set. And there's the real research problem. For what sets K, can you tell me if I observe a vector, I have a vector in K, but I observe noisy observations of that vector, how can I approximate it in some LQ norm? Give me an algorithm or describe to me the best approximation. That we don't know. Now, for LP balls, we know if K is LP, we now know how to do that. And I think it was known in expectation by Donahoe and what's the other author?
Johnson.
Not Johnstone, but Donahoe and somebody else. McGibbon. There's a paper by Donahoe and McGibbon how to do it in expectation, but to do it in probability is quite complicated. So I think this is a fundamental question. I mean, and this is a trivial question. You have vectors. I mean, right? You just have a vector functions and you have noisy observations. How do you denoise? And it depends on the norm you're using, and it depends on the assumption you have of the vector. Do you see what I'm saying?
Yeah, yeah,
Just
sure.
at
Yeah,
that problem for vectors, and if you could solve that problem, you could do a lot.
yeah, this is kind of understandable. Yeah.
Yeah.
Okay, other questions? So if there is no question, then Ron, thank you very much for giving us a talk. And I think it was very interesting and matches very well what we are doing in the seminar.
Oh,
So,
okay.
thank you very
Well,
much.
if I had another hour, I could have given more details and did a better job. But Volodya, if you ever want to have some Zooms over this subject and related subjects, and sampling and other things, we're happy to do it.
Ron, yeah, sure. Ron,
Contact by email.
Yeah, just send me by email time and because now we do not have a problem with time, so just let me know and I will, we'll connect and we'll do that.
All right.
I'm interested
Thank
in
you, Volodya.
Yeah, thank you,
Bye to
Ron.
everybody. Okay,
Okay.
bye.
Bye-bye. Thank
Bye.
you.